This is our first lesson in Unit 1011, where we are looking at continuous probability distributions rather than discrete probability distributions that we've been looking at up until now. So what we want to be able to do at the end of this lesson is to recognize the difference between a discrete and a continuous random variable. We are going to look at some of these distributions, and we're going to look at some terminology we're going to use to describe the shapes of these distributions. And we want to look at the relationship between the mean, the median, and the mode of a data set and what the shape of the distribution is. Hopefully we'll be able, by the end, to be able to determine the shape of the distribution without actually graphing the probability distribution or the frequency distribution. And we're going to get lots of practice along the way at creating histograms from our distributions. So first off, discrete versus continuous variables. And we talked about this a little bit when we talked about discrete variables. We said that a discrete variable or a discrete random variable can only take on a finite set of whole number values. So the classic example might be something like counting the number of red cars on the road. We can easily have 10 cars, we can have 12 cars, we could have 11 cars. We can't have 11 and a half or 11 and a third or anything like that. Okay? And it's unlikely that the number of cars is going to be infinity or something like that. So we're limited in the range of values that we can get, and also what numbers can be in that range. We can only really have whole numbers. Continuous variable can take on any value. Now, there are some caveats when we say any value, but an example might be if we wanted to measure the speed of one of these cars. It could be one of the red cars that we counted earlier. So if we're measuring the speed, we could measure a speed of 50 miles an hour, or 55 miles an hour, or 52.3, or 53 and a third, or something like that. So any of these possible decimal or fraction values are valid values for the speed of this car. Now, it's highly unlikely that our car seat, velocity or speed is going to take on a value like 200,000 miles per hour. And our range of values can't go up to, say, infinity or something like that. But in between putting a sort of a sensible upper limit and a sensible lower limit, we can have any sort of values that are determined by how accurately we can measure it. Okay? Now what we're going to want to do is make frequency distributions for continuous random variables. And these can be made by counting the number of values that fall into a chosen range. So as we're doing this, we're going to take, because our variable can take on any value that we want, we sort of have to say, I'm going to count the number of values in a particular range and use that to calculate my frequency. Okay? The size of the range is up to us, but it's often referred to as the bin width or the bucket size. And we'll encounter that term in a practical situation when we make a histogram. And what is a histogram? It's basically just a graph of the frequency distribution of a continuous variable. So if we make a graph of these distributions, we are going to get some particular kinds of shapes coming out here. So we are going to divide these into sort of 4 general categories. We are going to have what is called the uniform distribution. And we've seen this before. This is the example that we've got a single die, we're rolling it, and we're counting the number of times each of our outcomes turns up. Okay? Because it's a single die, all of our frequencies are approximately equally likely, or our frequencies are all approximately the same. We expect this because our probabilities are all equally likely. Okay? The probability of getting a 1, a 2, a 3, or 4, or so on. Okay? So what we see in a uniform distribution is that our distribution is symmetric, which means sort of the left side of it looks pretty much the same as the right side. And we don't see what we call a peak in the distribution. There's no value that sort of seems to be more likely than any of the other values. If we're considering the example of this die rolling game, what is the variable that we're investigating here, is it continuous or is it discrete? do we think? It's discrete. Yes, we can only get 1, 2, 3, 4, 5, or 6. So this is actually not a continuous distribution. This is a, I'll just say here, it's a discrete distribution, or a distribution for a discrete variable. And it changes how your graph looks if you're using a discrete variable and or a continuous variable. Notice that when we label each of these bars in our graph here, we are labeling sort of the center of each bar. Let's just say each bar is labeled. Okay. So we are counting each time a 6 comes up, or each time a 5 comes up, or so on and so on. Okay. And we could have spaces, I should say, could have spaces between the bars. Because there's a distinct separation between our 1 and our 2. Okay? We have the probability, or the frequency of 1, the frequency of getting 2, and sort of nothing in between them. So we could separate the bars a little bit on this one. Okay? Our next distribution, what is the textbook calls mound-shaped, more commonly referred to as a normal distribution or a bell curve. Okay? This comes up a whole lot. Okay, you'll see this over and over again in natural systems. So a normal distribution or a mound-shaped distribution is symmetric. It's got a big peak in the middle and 2 sort of tails coming off to either side, where the frequency decreases as we go to very small sums or very, very large sums in this case. In this distribution, is our variable discrete or continuous? What do we think? Okay. It is still discrete. Okay? We can get a 2, we can get a 3, we can get a 4. We can't get a 3.5 if we add together the sums that are on 2 dice. So this one is, again, discrete. Okay? Now, we can have a discrete, we can have the frequency distribution for a discrete variable can take on this mound shape. The frequency distribution for a continuous variable can take on the same sort of look. Okay? So these shapes are just ways of describing the graph. They're not sort of exclusive to either discrete or continuous variables. Our next one here, what we call U-shaped, or is often called bimodal. Okay? There are 2 modes or peaks in the distribution, and the mode just means the most frequent number. Or value. It's like most frequent value. Okay? So there are 2 modes or peaks in the distribution. The peaks do not have to be the same height. One can be bigger than the other, but there are 2 recognizable peaks, so it doesn't have to be symmetric. What we're plotting here are scores in a game of spider solitaire. Okay, we've got the scores running from 400 up to 900. Do you think this variable is discrete or continuous? It's a bit of a tricky one. What do you think? Got a 50-50 chance of being right here. Okay? They have graphed them as though they are continuous, correct? Because what we're saying is that you can have a whole, your score can take on almost any kind of value in between the upper value and the lower value here. Now, that isn't entirely correct. It could be that the way the scoring system works, you can only get half points, or you can only get single points. But because it can take on so many different values, we're treating it as continuous in this case. So there's a slight difference in how our graph is made when we are doing a continuous variable here. When we're labeling our axes, notice that the numbers here appear at the beginnings and at the ends of the individual bars. Okay? So each bar is not labeled as it was with a discrete variable. We are limiting sort of the ranges here. So if we take a specific bar here, like this first one, what is in that bar are all the score values that are between 400 and 450. Okay? rather than corresponding to a single value of the score. And then let's say point out that the edges of the bars are labeled. So the idea here is that our score values run continuously along that x-axis, and we're just sort of picking certain ranges where we're calculating them. So this graph here would have a bin size or a bucket size of 50. Okay. Okay. As well, if we're plotting a continuous variable, there should be no spaces between these bars, because our first bar goes from 400 to 450. Our second one goes from 450 to 500. There's no interval in between. All of our values have to fit into one of these bars, so we can't have these things spaced out. Okay. Finally, we have what are called skewed distributions. So these are basically normal distributions or mound-shaped distributions that have kind of been pulled to one side. Okay, it's like a normal distribution. We have a recognizable peak, but one of the tails has been sort of extended. So in this one, our left tail has kind of been pulled out and made bigger, so we call this left skewed. And this one over here, the right side, it's like this tail has been pulled out and extended, or we have more stuff on the right than we would expect, so we call this a right skewed distribution. Okay. And again, these are both examples. They have done the graphing for continuous variables. Okay. Notice again, when we're looking at our scores here, it's the edges of each of these bins that are labeled here. So those are the shapes of distributions, okay, that we're going to be using. What do you need to be able to calculate? Well, you need to be able to calculate the mean, the median, and the mode. And I'll just remind you of what these calculations are, and you'll get a lot of practice working on them as you go through the learning guide. The mean is just the average value. Take all your numbers, add them up, divide by the number of numbers. The median is the middle value if they are written in order. So you take your list, you sort them in increasing order, you look for the value in the middle. If you don't have a single value in the middle, you take the average of the two values that are on either side of the middle. The mode is the value that occurs most frequently in your list, usually corresponds to the peak of the distribution. And what you want to be able to do is, by comparing the values of the mean, the median, and the mode, you want to be able to figure out the shape of the distribution of this data set without actually doing the graphing. But again, you'll get lots of practice as you do that, working through the activities in boxes A and B.